And so on to our final lesson in this topic of physics, using physics to make things work, is something called circular motion. Okay, so that's what we're going to be looking at. And this isn't a particularly easy topic. What you can do is you can try to either understand what it is I'm talking about in this next slide, or you can just remember it. Basically, it might be that actually being able to explain it in these terms is a bit difficult, and you wouldn't have to for the exam. But I want to make you understand why we get a certain thing happening in circles. So the first thing to understand is that velocity, return to P1, is speed in a particular direction. That's important. Speed doesn't have direction, velocity does. So let's say you are travelling at a speed of 2 meters per second in that particular direction, and you then changed your direction slightly, so you're moving in that direction. Okay, sorry, I'll draw that a bit better. So let's say you're going in that direction, and that was 2, and then you changed and went in that direction. Okay, also 2. You wouldn't have changed your speed, but you would have changed your velocity. Okay, and that change in velocity, because there's a change in direction, it would be classed as being as accelerating. Okay, so even though the speed hasn't changed, the velocity has, and that means it's accelerating. And that's just because velocity considers direction as well, and that helps us to understand a bit about circular motion. So if we consider I know, let's say Earth. Okay, we've got Earth in the centre, and if we consider the motion of the moon around the Earth, so if I just draw in, so if it was here, okay, and moving round, it might be going in this direction. If I then look at it further on, okay, maybe more like this, then here, like this, and here, something like that, and then bringing it round to here, it might be moved something more like that. Okay, now all of this, it's not a great diagram, just change that slightly, it should maybe be a bit more like that. Okay, all of this is the direction of travel, so you can see it's constantly changing. Okay, so in this case, once things move in a circle, the velocity is constantly changing. Okay, so it's actually accelerating, and I'm going to try and persuade you in a moment that it's always accelerating towards the centre, or in this case to the Earth. Okay, so if I have a look at let's say these first two velocity vectors, so have a look at that one, and then I'm just going to draw the one next to it, which was going something like this, and then the green one, which was going something like this, the purple one going something like that, okay, and then the white one going something like that. Okay, what we can do is we can look at the difference between, so these are just like points in time basically, so this might be, I don't know, after 1 day, this might be after 5 days, 8 days, etc. Okay, what we can do, we can look at these points in time, okay, and we can see how the velocity has changed between them. Okay, so if I look at this first one, the velocity has changed in this direction. Okay, and the second one kind of like that, third one like that, fourth one like that. Okay, and this indicates the force that's acting on it, because a force, if we go back to Newton, only a force can cause a change in direction. Okay, so in this case, if we look at this, the force for the first one must be acting somewhere like that. Sorry, ignore that one. The force of the first one must be acting something like that. The force that's causing it to change the green one, and all I'm doing is I'm copying these forces that cause the change in velocity over to here. Purple one, it's acting something like that, and the white one is acting something like that. Okay, can you see how these are always pointing into the center? Okay, so there must be a force, okay, going into the center that keeps the object in a circle, okay, and keeps it going in circular motion, even though it's always accelerating. There is a force, and this force is called centripetal force. There's another force that sounds similar. We'll discuss that later on. Okay, so it's centripetal force. So this is the force that pulls objects, acts on objects, pulls them to the center of the circle, and it means because there's a force acting, okay, the velocity keeps on changing, the direction of the velocity, not the speed, okay, the direction of the velocity keeps on changing, so objects are constantly accelerating towards the center of a circle. Okay. So you can see this here, okay. When the object is moving this way, okay, the centripetal force is acting here, okay, at right angles. When the object's moving here, the centripetal force is acting here, so it's always acting towards the center of the circle. Alright, so it's constantly being pulled and constantly accelerating towards the center of the circle. Okay, and it maintains this idea of circular motion. So it might be a car going around a roundabout, it might be a moon orbiting a planet. Okay, so this is an example. We'll do this practical on Monday. When you have a ball on a string, okay, we've got this centripetal force, okay, that would be acting towards your hands, and you can actually feel that force when you're swinging it. Yeah, you can feel the force being exerted. Okay, so that's pulling towards there, okay, and the object is moving in that direction, and then again, you know, here, force, the centripetal force would be here, the object moving in direction, so constantly accelerating because the direction is changing, not the speed. Okay, so if, for example, you got rid of that force, so you're spinning it around, okay, and then the string snaps, you can see here it snaps, okay, that force is no longer acting, okay, there is no longer that centripetal force acting towards the center, and the object just flies off along its path of travel, okay. It would be travelling that way, okay, it just flies off there. And you probably know that, you can probably think of examples of when that's happened. Okay, so we'll have a look at things. So, in this case, the car's going round a bend or a roundabout, okay? So there must be a centripetal force allowing it to maintain that circular motion, and that centripetal force must be acting towards the centre of, say, the roundabout. Okay, in that case, the centripetal force is the friction of the tyres on the road. In the next case, okay, the Earth is moving around the Sun. Okay, so constantly accelerating round. Okay, and the centripetal force is acting towards the centre, so that would be, in this case, gravity. And we can also get, if we have a look at an atom, so electrons going around nuclei, okay, the centripetal force is an electrostatic force, okay, between the positive protons and the negative electron. Okay. Now, what a lot of people think, okay, is that let's say if you are going round a roundabout, okay, you feel like the force is actually pushing you outwards. Okay, so there's your car, you're going round the roundabout. Okay, it feels like the force is pushing outwards. That's not an actual force, okay, and this is the reason. Alright? So, as we said before, Newton's first law, you will continue moving with the same velocity unless there is a net force acting on you. Okay? So, the passenger, and it's important that it is the passenger in the car, yeah, when they're going around the corner, okay, they would continue moving straight on, okay? Remember, the centripetal force is acting on the tyres, in this case it's friction. Alright, so it's the force of the door that actually keeps you in, because there's no force on you, the force is on here, okay, the tyres, between the tyres and the road. Okay, so you feel like you've been flung out of the car almost, okay, but the door keeps you there. Alright, that's what you experience, that's what you feel, but and they call this centrifugal force, but it's not an actual force, it doesn't exist, okay, it's just a feeling that you are moving towards the edge of something. It's the same as let's say when you're on some of those swings in like a theme park, and they've got that central thing, okay, and the swings are like this and they're moving round, okay, in a circle, and you feel like you're about to fly off that way, okay. That's not the case, that's just what you feel, because there is not that force acting on you, that centripetal force acting on, well, it'd probably be this, okay, this and the bars. Okay, so if we have this example, ball and string is swung in a vertical circle. Alright, the string happens to break when it's parallel to the ground and the ball is moving up. Okay, so the string breaks here. Which path does the ball follow? Would it continue to move in its circle? Kind of away from its circle, but kind of moving around. Okay. Would it move in a straight line, or would it move outwards? Have a think. And the answer would be C. Okay, because as soon as that string breaks, there's no force acting, there's no centripetal force. Okay, it couldn't move like this or like this because there's no force acting on it, so it cannot change its direction. Okay, so it must go like that. Alright, it would fly off at that angle.